you very much. Thank you very much for the invitation and for the opportunity to lecture here. It's a great pleasure. So as you heard, the title of my talk is Symplectic Homology and Applications. And this symplectic homology is going to be a version of Floer homology along the lines explained by Mihai this morning, which will be constructed for open manifolds. Right? So first of all, I would like to indicate a few references. So Mihai said that I would indicate some web address for some lectures. So that's HTTP, homepages, .abdn, like Aberdeen, ac.uk, Kedra, that's Jarek Kedra's pages, oops, LMS, right? So that's some general lectures on constructions of Floer homology, mainly in compact setting. So this complements the references that Mihai has indicated. And concerning symplectic homology, there's the founding papers of Floer, Hofer, Chilibach, and Vysotsky, and also Viterbo. So in various combinations they have written together. Viterbo has one paper which was extremely influential in GAFA, 99. And in recent years, there's been an extremely influential survey paper by Paul Seidel, 2007, which is called A Biased View of Symplectic cohomology for a change. Right. So whatever I'm going to, there's other references, but whatever I'm going to say essentially builds on the work of these great guys. So I want to start with two driving questions. One is the reformulation of what's known as the Weinstein conjecture. And in the so I'm going to state it as follows. Does any compact contact manifold carry a closed orbit for an arbitrary vector field, Reb vector field? Yeah. So some definitions are in order here. A contact manifold is an odd-dimensional manifold, yeah, endowed with a hyperplane distribution. So that's a hyperplane distribution. That is maximally non-integrable. Non-integrable. So this means that, of course, any hyperplane distribution can locally, we can write it as the kernel of a one form, and we require that alpha wedge d alpha to the maximal power, which makes sense, is non-zero. Right? So usually, so in what follows, I'll assume that such an expression is valid globally. And this is just a topological condition. It means that the contact structure, this is called the contact structure, is co-orientable, right? Xi is kernel of alpha globally. Yeah. So these are kind of odd dimensional analog, not analog, sisters of symplectic manifolds. And an alpha like here is called a contact form. Contact form. Whoops. And this determines what's called a Reb vector field. Yeah. R alpha, which is defined by the following two conditions. First of all, d alpha is going to be non-degenerate on Xi, and it's going to be, it's going to have a one-dimensional kernel. And we want this to be the generator of that one-dimensional kernel. Yeah? And then we normalize that by the condition that alpha evaluates to 1 on R alpha. Okay? So as an example, right? Pick such a hypersurface in R2n, right? Such that the Liouville form, which is which is 1/2 sum of xi dyi minus yi dxi restricts to a contact form. Yeah? On M. So this is called a restricted contact type hypersurface. Type hypersurface. Of course, such a hypersurface can be presented as the energy level of some Hamiltonian, which is time independent, right? If M is, say, H inverse of 0, with 0 regular level, and this H being some function on R2n with values in R, then you can check that XH is going to be a multiple of R alpha. Right? Is a multiple, non-zero, multiple by some function of R alpha. Right? By some function. Function, say, f. Right? And therefore, you see that the dynamics of this vector field here on some arbitrary contact manifold are a way to encode Hamiltonian dynamics, right? But except that it's in a slightly more abstract setting. Right? This will hold regardless of your choice of Hamiltonian, which admits the hypersurface as a regular energy level. It's just the function that's going to change if you change the Hamiltonian. But this property of being a multiple of the Reb vector field is still going to hold, right? So you can view this question as an analog of the Arnold conjecture. The Arnold conjecture was asking for lots of closed orbits, periodic orbits of given period, right? This is asking for at least one periodic orbit on a given energy level. Okay? So these two kind of trade each other, right? So note Arnold conjecture it's about fixed period. And Weinstein conjecture is about fixed energy level. Right? So one theorem so this has been proved for in dimension 3 by Taus. And in arbitrary dimension, there is no general proof. In arbitrary dimensions, it's still open. Yet, the groundbreaking results, yet it's proved for many hypersurfaces. For many hypersurfaces. Right? And the groundbreaking result here was the one by Viterbo, said that, who proved that if M in R2N is a contact type hypersurface, this meaning a slightly general condition than that of restricted contact type, namely that there exists some lambda primitive of the symplectic form, of the standard symplectic form, defined in the neighborhood of M, and such that it restricts to a contact form on M, then the Weinstein conjecture is true. So any such energy level over Hamiltonian carries a closed orbit for the corresponding Reb vector field. These closed orbits are also called closed characteristics. So I'm going to give you more instances of that, and in particular, give you a proof of this theorem, hopefully today. This is one circle of questions to which symplectic homology, the invariant that I'm going to define, will be able to answer. And the second type of questions that I want to mention is something that already appeared in Mihai's lectures, and that's the existence obstructions to Lagrangian embeddings. Yeah? So given some L, right, and also some symplectic manifold, which is exact, yeah, does there exist to begin with a Lagrangian embedding of L into W, yeah? And this means that the symplectic form has to vanish on L. And also, does there exist an exact Lagrangian embedding i.e. the one form restricted to L is an exact one form. Of course, it is closed because its differential is omega and it's supposed to restrict to 0, right? So lambda is a closed one form when restricted to L. So symplectic homology is going to be able to answer questions in the second vein, yeah, about existence or non-existence of exact Lagrangian embeddings, right? So the first groundbreaking result here was that of Gromov, who proved that there is no exact Lagrangian in R2n, endowed with the standard Liouville form. Okay. So symplectic homology, as I will define it, will apply to actually manifolds, which in particular are going to be exact, right? Like the one here, like R2n with the standard symplectic form and the standard primitive of the symplectic form, right? But I want to describe now a construction that is associated, that associates to a contact manifold a symplectic manifold. That's called symplectization, right? And that symplectic manifold is naturally exact, right? Just to serve as a kind of heuristic motivation that the world of exact manifolds is relevant maybe to contact geometry. Yeah? So, example, symplectization. Of a contact manifold. So we take M psi to be a contact manifold, and let me define SM, like symplectization, to be the following subset of T star M. Yeah? So it's going to be, say, the X and P in T star M such that P the kernel of P is psi at X, or, and that's it. Yeah? So that's a subset in T star N. Right. So I have a hyperplane distribution in M, and P is a covector, so it's a one form at that point, and I can consider all those who vanish on psi, right? And the fact is that lambda, or rather, I would say, the canonical symplectic form, which is dp wedge with my notation, it would be dx, right, on T star M, restricts to a symplectic form on SM. Yeah? So this is a kind of intrinsic way of defining the symplectization. A much more explicit way can be the following. Note, if psi is the kernel of alpha, right? Define, or rather consider, say 0 infinity cross M with D of R alpha. Yeah, this is a symplectic manifold. And Sm, if you wish, is symplectomorphic to two copies of that. Two copies of this. 0 infinity cross M. So why two copies? It's because in this case, it means that I have by choosing such an alpha, I have chosen a co-orientation for psi, right? And I have to consider, here I have not specified whether in that direction P is positive or negative, right? So if psi is co-oriented, this has two connected components, right? And these are exactly two copies of that. So from now on, I will actually refer to the symplectization as to this guy, or rather, in the co-oriented case, to one connected component of this. Yeah? And you see that this thing is exact, right? This is an exact symplectic manifold. Right? So now it's time to define Liouville domains. And these are going to be my the main players in these lectures. So definition. Yeah? A Liouville domain is a symplectic manifold with exact symplectic form, and lambda is part of the data. It's not that I'm saying that there is some lambda. Rather, the Liouville domain is W and lambda, if you wish, such that d lambda is symplectic, and such that lambda restricted to the boundary of W is a contact form, yeah, which defines, so contact form means lambda exterior d lambda to maximal power non-zero, so in particular it defines a volume form on the boundary, and I want this volume form to define the same orientation as the boundary orientation. Same, which defines the boundary orientation. Of d W. Alternatively, equivalently, whenever I have lambda, I can define its dual, so define what's called the Liouville vector field, Z by omega, or rather, d lambda of Z dot is lambda, the dual vector field to lambda. Then we require that Z be transverse to the boundary and pointing outwards. To be transverse and to point outwards along the boundary. Yeah. So the examples. For example, I should have said, I want it to be exact. I want it to be compact with boundary, right? Sorry. I mean, forms may be exact and still not have any boundary. I want it to be compact with boundary. Yeah? So examples. Here's B to n of some radius, yeah, in R to n. Here the standard symplectic form is sum of dxi dyi, and the standard primitive is what I wrote before, sum of xi dyi minus yi dxi. Right? And then the Liouville vector field, whoops, is at a point z is, I believe, 1/2 of z. Yeah? So it's the Euler field, but with a factor 1/2 in front. Yeah? Another important example is take some Riemannian manifold, and consider the unit cotangent bundle, dt star L, meaning not rather unit, but the unit ball cotangent bundle. So it would be the QPs with norm of P at most 1, or R, it doesn't matter. Yeah? So in this case, we're dealing with the standard symplectic form, which is sum of dpi dqi in local coordinates, and it makes sense globally. The Liouville one form is sum of pi dqi, and this is exactly what Alberto has written in his lectures, right? You take, it acts by taking a tangent vector at some point qp, projecting it to the base in order to obtain a tangent vector and evaluating p. That's what it does. Right? And then the Liouville vector field at a point qp is just going to be p itself. Right? It's going to point along the fiber. Right? And you see that it's going to be transverse and outward pointing along the boundary. And another example, 3, or, yeah. Let me write 1, 2, and 3. That's that of Stein domains, so something coming from complex analysis. So a Stein domain is a complex manifold right? So that's a complex structure, right? And phi is what's called a plurisubharmonic function. So that's compact with boundary. Yeah, it's a plurisubharmonic function. I'm going to say what that means, such that phi is, so sorry, I should write maybe minus infinity 0, yeah? And the boundary is phi inverse of 0, regular level. And plurisubharmonic means the following. It means that if we consider dc phi, which is d phi circ j, right, then minus d dc phi of VJV is positive for every V, which is non-zero. Yeah. So this in particular implies that this thing, which I call omega phi, is a symplectic form. The primitive is going to be minus dc phi. And if you compute, it turns out that z, right? So lambda is minus dc phi. And if you compute, it turns out that z is the gradient of phi. With respect to what metric? Well, with respect to the metric, omega phi of dot j dot, and this is a formula that you already have seen, right? So, yeah, these are other examples, large class of. And there's also a more flexible notion called Weinstein domain, but I will not give the definition, and it's more appropriated to symplectic topology. But now, if I start with this example, so we know that Stein domains are kind of regular sublevel sets in Stein manifolds, right? So such a Stein domain is always, included in a Stein manifold, right? This being the same, like wj and phi, and now phi, I just require to take values in R to be proper and bounded from below. Proper, of course, plurisubharmonic, proper, and bounded from below. Right? That's the definition of a Stein manifold, one of the definitions. So there's this process in which, out of some domain here, right, there's something bigger, which in the case of a Stein manifold may have some topology, right, of enlarging and passing from something with boundary to something which does not have boundary, right? So we're going to do this right now in order to build out of a Liouville domain a manifold which does not have boundary. And how are we going to do that? Well, we're going to use the symplectization, which is the thing I'm erasing right now. Yeah? So note that given a Liouville domain, right, the flow of Z is conformally expanding. Meaning that if I write the flow by phi z at time t and pull back the symplectic form, I get e to the t times the symplectic form. Right? And therefore, I get a symplectic diffeomorphism from, say, zero infinity, no, not zero infinity, from 0, 1 times boundary to a neighborhood, open neighborhood of the boundary. And this diffeomorphism takes a coordinate r and a point x and sends it to flow of z at time logarithm of r of x. So typically, this is my domain here, and the vector field points outwards. Right? And since it points outwards everywhere along the boundary, it means that the flow is defined in arbitrary negative time. So this expression does make sense, right? And of course, it's going to establish some diffeomorphism between this set and whatever it does here, right? And because of this formula, you can just check that this is a symplectic diffeomorphism, where here I have, so let me write this map like phi, yeah? And then it's not only symplectic, but if you pull back the Liouville form, the primitive of the symplectic form, you get R times alpha, with alpha being the restriction to the boundary. Okay? So that means that for a given Liouville domain, actually a very large neighborhood of the boundary is identified with half of the symplectization, right? And hence, I can attach the other half and obtain a manifold which does not have boundary. Right? So denote W hat to be W union 1 infinity cross boundary. Yeah? Then here I have d over alpha, and here I have omega. And the gluing is given through this map phi. And what's the outcome of this construction? Well, in the case of the ball, unsurprisingly, you get, by this process, R2n itself, right? And in the case of the unit ball bundle, you get, by this process, the full cotangent bundle, right? So now, yes. No, no. It is, if you wish, so it is what's called Weinstein, right? So it, this thing has how should I put it? So you have here a symplectic form which is, I mean, you have the Liouville form, lambda standard, which is sum of pi dqi. And then you also have a function which to qp associates norm p squared over 2, right? This function is, of course, a Lyapunov function for the corresponding vector field. It's just not Morse, right? You can perturb it in order to turn it into a Morse function, which is going to have critical points of index at most n. Yeah? So such a pair, Liouville form, and then function which is Lyapunov for the Liouville vector field, and which has critical points of index at most n, is called a Weinstein manifold. So it has this structure naturally that comes to you after perturbing a little bit. Does this answer the question? Yeah. But indeed, I mean, there's something, I understand, there's something perturbing if I talk about Stein manifolds, because it's supposed to be a very rigid structure. Why? I mean, we have that complex structure there. Whereas in the realm of symplectic manifolds, we're dealing with almost complex structure. We flexibilize that very much. But it turns out that, as a matter of fact, in this case, if we allow deformations of complex structures through almost complex structures, the two notions are equivalent. And that's a very deep theorem of Eliashberg, which I don't want to, but the idea is whenever we want to turn something from complex geometry into something symplectic, the almost complex structure is going to be allowed to vary through almost complex structures, right? So, let me see what my plan is here. Yeah. So symplectic homology. Right? So we are going to associate, the idea is the following. We're going to associate to a Liouville domain we're going to associate a group, which I'll denote like this. This is going to be an abelian group, and actually more, it's going to be a ring with unit. A ring with unit. Yeah? With the following properties. With the following properties. First of all, this thing is to be thought of as being an extension of the homology of the manifold. Namely, there's going to be a map from the relative homology of the manifold to symplectic homology. I will actually not delve into details about the grading, but what I'm writing is true for a certain convention. And if you wanted to refer to the structure of ring with unit, it's actually much more convenient to view this part as being the cohomology of the manifold itself. And this is going to be a map of rings, yeah? Homomorphism of rings with unit, meaning that the unit here is going to be sent to the unit here. Okay? That's the first property. I'm wondering, maybe not to make it more convenient, I'm going to erase this blackboard just to have all the properties at the same place. This was just two examples of what adding this half symplectization does. Second, whenever for any, so how should I, no, sorry. Property 2, if the boundary does not carry any closed characteristic, then this map is an isomorphism. I'm going to call it C star. Then C star is an isomorphism. Yeah? And this is this was Viterbo's idea to approach from an algebraic point of view the Weinstein conjecture. If ever you're able to prove that this map is not an isomorphism, right, you conclude that you must have some closed characteristic on the boundary, right? So you prove the Weinstein conjecture. 3. Yes. Indeed. N is the dimensional of 2n is the dimension of W. It's just a uniform shift. Yes, which comes from some conventions on Conley-Zender index. Sorry? Indeed so. Thank you. Thank you. Yes. The third property is a kind of functoriality. And this says the following. If V inside W is a Liouville subdomain, or exact inclusion, meaning that the primitive restricts to V to a Liouville form, yeah, i.e. it's the same as saying that the primitive restricts to the boundary to a contact form such that, or rather, yeah, Z restricted to the boundary of V is transverse and points outwards of V. Outwards. Yeah. Then there exists a map which goes the other way around, right? So let me think. How should I? I'm going to write it this way. You have the map on cohomology going from the bigger to the smaller. Yeah. And symplectic homology is an extension of cohomology. And you have such a map which makes it into a commutative diagram, right? And this is the main result in Viterbo's 99 paper. Yeah? So let me go on with the properties. Map of rings. Yes. Map of rings. With unit. Yep. So addendum to the third property, 3 bis. Same is true if V, if the boundary of V does not possess any closed characteristic. Except that in that case, you know what this term is, and that map is going to be the identity, right? So you have this, you have this. Maybe I should write C star, which is an isomorphism. And you have this commutative diagram. Okay. And then 4, one can define also define a relative symplectic homology group. Homology group. Yeah? So this one fits in a long exact sequence associated to the pair. Yeah? And here you have relative cohomology. Yeah? You have and you have these maps. Yeah? So all the squares in this are commutative. Yeah? And that's something that we are writing with Cauchy-Libak. Right? So the way I like to present this is that just like singular cohomology, yeah, is a cohomology theory, right? Meaning that you can define the cohomology of a pair, right? You have this long exact sequence of a pair. There's also something called excision, which is very important in computations, right? In the same way, symplectic homology is an extension of differential topology, right? Which will feature the same formal properties. In particular, it's going to satisfy suitable analogues of the Eilenberg-Steenrod axioms for a cohomology theory. Yeah? And it's going to extend differential topology of your manifold by taking into account the dynamics on the boundary. Right? That's the philosophy. I mean mine. Yeah, so point of view. Yeah, so I've ended up writing in Arabic here. It's so point of view. Symplectic homology is extension of differential topology, of maybe singular cohomology, just like symplectic topology is a subtle extension of differential topology. Right? And the main players in this story are the dynamics on the boundary, because we know that if on the boundary, and holomorphic curves, of course. Yeah? Okay. So like with all great mathematical objects, it's supposed to satisfy all these fantastic properties, so it must be very complicated, and on the contrary, it's extremely simple. So the definition goes as follows. So the remark is the following. Let's draw the following schematic diagram. Here I have the boundary, which corresponds on the R scale to R equals 1, right? This is W itself, yeah? And this is the part that we have added. Yeah? So let me choose a Hamiltonian, which is going to be of this form. So consider, the idea is the following. Consider the following class of Hamiltonians. So it's going to be Hamiltonians which, for the purposes of Floer homology, can be thought of as being time-dependent but periodic in time. Yeah? Such that restricted to S1 cross W, there's negative, independent of time, t is the variable here, and C2 small, Morse function. So that's what I drew here, something that's negative and tiny. And then I want them to have non-degenerate one-periodic orbits, non-degenerate, in the sense explained by Mihai, namely, well, I wonder whether I want them to be non-degenerate. Let me not write this for the time being. Yeah. But ultimately, the things for which Floer homology is going to be defined are those for which the Hamiltonian action functional is a non-degenerate function, right? Has non-degenerate critical points. So, but let me not include that in the definition of this class. Let me include this here, which means that H of T, R, and X is, say, some AR plus B for R large enough, yeah, with A positive, yeah, and A different from the period of a closed characteristic. So a particular example of such a Hamiltonian would be the following example. Say H of T, H independent of time, everywhere, time, and H of T Rx equal to some H of R, right? For R immediately in the half symplectization that we have added, right? So let's compute what the Hamiltonian vector field is here, right? Then the Hamiltonian vector field, which with my conventions is defined by the opposite convention as previously, namely omega of xh dot is equal to dh and not minus dh. Sorry for that, but if I do not stick to it, I may write nonsense on the blackboard because I'm so much used to it. Right? So we compute on 1 infinity, cross boundary, h is h of r, and hence I get d of r alpha of xh dot equals h prime of r dr. Right? And from this, you obtain that xh is minus h prime of r times r alpha. Yeah. So what has happened here? It means because the Hamiltonian vector field is proportional by the slope of the Hamiltonian to the Reb vector field, it means that if I look at one periodic orbit, which is what Floer homology knows how to do, right? I'm fixing the period of the orbits. If I look at one periodic orbit, say for a function h with increasing slope up to a, I'll be seeing characteristics of period up to a. And then I can let a to be larger, larger, and larger. Right? So, so the definition is the following, and this is Viterbo's definition. Define SH star of W to be the limit as A goes to infinity. Yeah, maybe I should write some A here. Of Floer homology of a Hamiltonian H, right? Or maybe HA, with HA in script SA, HA, right? And with non-degenerate one periodic orbit. Yeah. That's it. But there's a lot to be said now, right? So what I'm implicitly saying here is that implicit here is that Floer homology of such a Hamiltonian is well defined. And I have to say something because Mihai was working in a compact setting, compact manifold, and here my manifold is non-compact. Yeah? And then I'm also saying that if A is smaller than A prime, then, and to simplify, if HA is smaller everywhere than HA prime, then there exists a map from between these things, HA prime. And then I take the direct limit as A goes to infinity. And of course, it's implicit, since I have written one Hamiltonian, it's also implicit that the result of this story depends only on the slope A, right? Also, and independent of only, and depending only on A, right? Only on A. So, but you see that morally, this object does the job, because if I think of such a Hamiltonian with slope, maximal slope A, it's going to see close characteristics up to period A. Of course, if it's independent of time, the condition that the one periodic orbits be non-degenerate is not satisfied, right? Because as soon as I have one, I can shift it around. It's independent of time. Never mind, you perturb tiny bit. Something happens, right? It's encoded in the construction. You don't have to worry too much at this point. It's Floer homology's way of taking into account orbits up to period A. And then as you let the slope, the maximal slope, go to infinity, you take all of them into account in some algebraic way. The result is what it is. So it's interesting to the extent to which you're able to compute in some interesting examples, right? So this is my, the next thing I want to say. So maybe because I'm still at the things that will have to be discussed, let me write here also the question of what type of almost complex structure should we use? Right? Because I've written just the Hamiltonian, and in the definition, of Floer homology, there's also an almost complex structure involved. Hopefully, the result does not depend on that. But nevertheless, the choice of almost complex structure will play a certain role. Yeah? But before going into the details of the definition, I want to explain two computations. Yeah? So, computations. Yeah? First of them is for balls. Yeah, and the result is 0. Which is very good news. Yeah? Because it tells you in particular, of course, that on the boundary of the ball there is a closed characteristic, but it's going to tell us more, right? It's going to, right after I explain why this is true, it's going to prove the Weinstein conjecture in R2n. Yeah? So the reason is the following. You proof of this, yeah? So implicit in Mihai's lecture was the following fact, that Floer homology for a Hamiltonian defined on a compact manifold without boundary, right, is isomorphic to singular homology of the manifold. Right? In particular, you can read this result in the following terms. Floer homology is independent on the choice of the Hamiltonian as long as you vary it on a compact set. Yeah? So Floer homology is of H is independent on H as long as the latter varies only inside a compact set. Yeah? Just like if you think of Morse homology, you pick some Morse function, you change the metric, the vector field is going to change, right? But as a matter of fact, the homology is going to be the same, right? Why is it going to be the same? Because each gradient vector field that you're going to pick is going to give rise to some cellular decomposition with the same number of cells, and homology is going to be cellular homology. Homology is going to be the same. But you can view that also as a kind of interpolation argument, right? You move from one metric to the other, understand what the accidents are along the way. You see that there's some bad connecting orbits, but as you cross them, nothing happens. There's also one way of understanding why Morse homology is independent on the choice of metric. And as a matter of fact, it's also independent on the choice of Morse function. Same argument, except that a little bit more complicated to put into practice. Yeah? So for the time being, I just want to leave it with this heuristic explanation of why this should hold. So therefore, if you accept it, then we can use on B2n hat, which is R2n, and which is also Cn, for a given slope A, and this A has to be different from the period of a closed characteristic on the boundary of the ball, right? And that is K pi R squared. Yeah? And these are the periods of closed characteristics. On the sphere of radius r. Yeah. So what Hamiltonian do I want to use? Well, let me use, instead of this, yeah, let me use this. Yeah. And what is it? This Hamiltonian here is h of t z equals a norm z square, and then I want it to be 0, say, at this value. So a norm z square, a norm z square, and for z equals to r, I want it to be 0, minus AR squared. And this is a smooth Hamiltonian. And here I've switched secretly between those coordinates, r and x, into coordinates z. Yeah? And it turns out that on Cn, because of that 1/2 factor in front of the vector field, right? The Liouville vector field was 1/2 z, right? Because of that, linear coordinate with respect to r is actually quadratic with respect to z. And that's why this Hamiltonian is genuinely smooth. It's a really good one. Yeah? And it has the following interesting property, that its only one periodic orbit is a single one, and that's the constant orbit at the origin. Yeah? So this has just one periodic orbit, namely constant equals 0. And this is non-degenerate because that's a quadratic form, which is non-degenerate. Okay? So it means that the Floer complex, which is for this Hamiltonian, the Floer complex for this Hamiltonian, az square minus ar square, has rank 1. And if you believe that this index functions as it should, right, namely that it is the index of that point, this is the index of the linearized Hamiltonian flow at the origin, right? Then you see that it is actually the Conley-Zander index of a path of the form, wow, now I'm going to get it wrong, absolutely. It's, yeah, this is going to grow, index grows linearly with A. I'm chickening out here. So it's something like the linearized flow is going to be something like e to the t a j, and then some diagonal matrix. Maybe this e to the t a j up to some factor. Yeah. And as A grows and you let T go from 0 to 1, because you're looking at one periodic orbit, this is going to have index larger and larger. Yeah? So this thing, although it's all the time non-zero, appears in different degrees. And hence, that map that we're trying to define there necessarily has to be 0, right? The non-zero generator is going to go to infinity, right? And therefore, in the direct limit, the result is going to be 0. Hence, the limit of these Floer homologies, Hamiltonians, is going to be 0 in each degree. And that's the computation. So you can take the computation of the linearized flow as an exercise, and I'm going to also do the exercise at home. Yeah? Okay. Good. Thanks. Which grows linearly with A. So, second computation. Oh, maybe, I don't know. Before the second computation, let me write an application, right? Application. The Weinstein conjecture holds in R to n for hypersurfaces of contact type. Yeah? Why is that? It's because if M, yeah, in R to n is such a hypersurface, has contact type, this is necessarily going to be separating, so there's going to be some domain that it bounds, right? And we can consider this inclusion, and according to property 3, I think, functoriality, you have a map as follows. You have a map going from B to n of some radius to the cohomology of W. That's an isomorphism, cohomology of W. That's cohomology of the ball, right? And you have this map. So this thing is 0, and this thing is an isomorphism in degree n. Of course, the map from H0 to H0 is going to be an isomorphism. And this is also an isomorphism. So it's not possible that an isomorphism factors through 0. No, I've said that this map holds, this map is constructed, yeah, is defined, even if either you are restricted contact type, so exact inclusion, or if you don't have any closed characteristic. Yeah? Okay? So that's contradiction, and this proves that this assumption of not having, with no closed characteristics. As a matter of fact, this also proves, so fact, which I'm probably going to develop a little bit more tomorrow, let me see. So symplectic homology vanishes if W is a Stein manifold, or a Stein domain, which is subcritical. Meaning, it has a plurisubharmonic function, which is Morse, and such that the index of any critical point is at most n minus 1. For a plurisubharmonic function, the index of all critical points is at most n. And if it's at most n minus 1, you say it's subcritical. And in that case, symplectic homology vanishes again. And this proves that the same conclusion is true in there. Right? So actually, Weinstein conjecture will hold for any manifold such that the symplectic homology vanishes. Yeah. And as a matter of fact, here's a theorem by Abu Zaid and Zeidel, which says that for any Stein domain, there exists another Stein domain which is diffeomorphic to it, such that W prime is diffeomorphic to W, and such that the symplectic homology of W prime is 0. So that's also related to the same kind of question. No, that statement. No, of course not. Of course not. If for any Stein domain W, there exists W prime such that blah. Of course, no. No, because Stein domain in general has topology in the middle dimension. So W prime cannot be subcritical in that case if it's diffeomorphic to it. Right? So it goes much beyond the subcritical case. That has nothing to do. I mean, this is like playing ping pong, and this this is wrestling. Okay. So the second computation relates to Alberto's talk, right? And this is what Alberto is going to prove in his lectures, namely that for the cotangent bundle, symplectic homology is isomorphic to the homology of the free loop space, which you denoted lambda L, right? You denoted it by what, lambda L. At least if, so that's free loop space, right? With Z2 coefficients, or with Z coefficients if L is spin and orientable, meaning that W1 is 0 and W2 is 0. Yeah. But what I'm going to use here now, so this is, I have to quote people because everyone is in the room here. So this is Viterbo, and then Salomon Weber, and then Nabondandolo Schwarz, right? And concerning this spin condition, here one has to quote Thomas Krug. From MIT. So the one thing that I want to, that I'm going to use in the vein of Viterbo, the original paper of Viterbo here, is that the homology of the free loop space is non-zero. Of course, the free loop space receives the manifold itself by embedding of constant loops. Every point in the manifold is sent to the constant loop that it represents. And this embedding, of course, has a right inverse, which is evaluation, right? So evaluation circ inclusion is the identity of L, and this shows that this map in homology is injective. Right? Hence, this map in homology is injective, and in particular, this thing, well, maybe, I mean, we knew that it's non-zero because it's a non-empty space, sorry. But anyway, yeah, I'm doing too much symplectic homology where things can vanish. So, this implies the following theorem, which already appeared, a theorem which was first proved by Gromov, and the proof here is that of Viterbo, namely that there is no exact Lagrangian embedding into R2n. Exact Lagrange embedding. Yeah. Proof. Whenever we have assume yes. Yes. Then there is the Weinstein neighborhood theorem. Which tells us that for a suitable choice of Riemannian metric on L, dt star L embeds into R2n, right? And the exactness, if the embedding of L into R2n is exact, then the primitive lambda standard, yeah, can be modified in the neighborhood of this dt star L, so that it restricts on dt star L to the canonical primitive. Yeah, that's a symplectic embedding. And this is a good exercise. Yeah? You just interpolate between two primitives of the same one form. And this tells you that up to having modified lambda on a compact set, lambda standard on a compact set, right? I have an embedding of an exact embedding of Liouville domains, right? Have exact embedding of Liouville domains. Right? dt star L inside some large ball. So let's write the same diagram as before. So I have here the symplectic homology. I have here the symplectic homology of the ball, which extends the cohomology, or say for this time I'll write the homology of the ball relative. Or, yeah, let me think. Maybe I'll write it like this. Hn minus star of the ball, right? And on the other side, I have Hn minus star of dt star L and the homology of the free loop space. So now there's this map, and as a matter of fact, this map is very interesting. If you think a little, yeah, it's embedded in the construction, and for now you just have to take it as is, as a claim. So here I'm using Poincaré duality in order to write relative homology with respect to the boundary of dt star L. And this I can identify with the homology shifted by n by the Thom isomorphism, right, of dt star L, or sorry, of L, of the base, right? And this map is actually just the inclusion. So it's in particular non-zero, right? And this map is also, now you reason, say, in degree star equals n. This map is an isomorphism. In degree n, this map is injective. You have the embedding of this thing inside here, and it factors through 0. And that's, again, a contradiction, right? So I personally like a lot this, this way of proving things, because it's a statement a priori about some rigidity property of some symplectic object. So it's a statement in symplectic topology. And you prove it by looking at that object which rests fundamentally on dynamics. Right? And I really think, like as an incentive to study this field, that this interplay between rigidity and dynamics is maybe the most exciting in the field. So I'll stop here.